Okay, welcome to today's tutorial. This is actually a week 4 tutorial, so we'll solve some problems from assignment 4. So just a minute. Okay, so one of the last week assignment. So most of these problems are actually from the lecture itself. So, for example, first problem, why quantum Hall states are incompressible. So that is yeah, and that has been also solved in the like one of the lecture itself. So once you calculate compressibility, it was calculated that compressibility, which is proportional to del v del p. So so the compressibility is proportional to k, let's say. I mean, compressibility is represented by k, which is proportional to del v del p, and if you derive that, uh, it will come out to be 0 for quantum Hall states. Of course, in this case, v is equivalent to area, v is the volume, so this is equivalent to area. We are dealing with the 2D electron gas when we discuss quantum Hall effect. So I am not deriving these things, and second question is derive the Kubo formula for Hall conductivity within a linear response theory. So some part of it I will derive, because I think this was not completely derived. Okay. And then the third question is draw a neat level diagram of the Corbino disk, discuss how it acts as a quantum pump, and explain quantization of Hall plateaus. So again, this is exactly from one of the lectures actually. Fourth question is also solved in the lecture itself. In fact, 5 A and B also solved. So the only thing that has not been explained in detail is that question number 2, and yeah, that is question number 2, and then I can also do some so I'll also do Landau level derivation for graphene, let's say. So 5A question, what it does is that so basically this was the derivation of tight binding model for graphene, tight binding Hamiltonian for graphene, and from that, in the low energy limit, if you expand around the key point, so for tight binding, so tight binding graphene will have some dispersion like this, something like this. It's not exactly like this, but yeah, there is another band in the below. Okay, exactly similar to the upper band, and this was the k point or k prime point, k or k prime, and then this was, let's say, gamma point, this was also gamma point, and somewhere here when at one point the band dispersion, so this is the energy, one point the band dispersion is parallel at a particular point actually, this is m point. Okay, and at the m point, uh, there is a, I mean, so you have del epsilon del k equal to 0, because this is a flat at a particular point at m, let's say m point. Okay, and yeah, so that was the tide bending dispersion, and around this point maybe so if the energy is typically around plus 10 volt to minus 10 volt roughly, it depends on the Hamiltonian parameter that you take, hopping elements, but it's about EV order basically. Now around this k point, around some very narrow energy range, let's say it might be at max 1 EV, let's say, around. Okay, so this part, this circular part will exactly look like something like this. So this can be very well approximated with the linear dispersion. Okay, linear dispersion. So in general we have a uh, Hamiltonian, tide bending Hamiltonian, which will look like something like so you must have found that Hamiltonian will be so 0, this is A basis, this is B basis. So before that, what is the graphene structure? So this is the graphene structure, honeycomb lattice. So A type atom, B type atom, and then again A type, B type, and then alternatively it goes on, right? So and then unit cell was something like this. So rhombus type of unit cell, or you can even think of there is a triangle unit cell. Okay, uh, okay. So the Hamiltonian was like f of k, f star of k, and 0. And so we had a nearest neighbor. So if you define the nearest neighbor something like this, a is the this distance is a, then so the nearest neighbor hopping vectors basically are given by root 3 by 2 half, delta 2 is given by again a root 3 by 2 minus half, and delta 3 is simply a minus root 3 and 0. Okay, so these are the hopping vectors, and in terms of this we have f of k expression is given by minus t, and so e to the power I kx into root 3 by 2 plus ky into a by 2 plus e to the power I simply. So these are basically sum over minus t into sum over I equal to 1 to 3 and to the power I k dot delta I. Okay, so this part I am writing here, and simply kx root 3 by 2 minus ky a by 2 and plus e to the power minus I root 3 kx a, right? So this is the fk, and you can do the f star k by taking complex conjugation. Okay, so this is the tide binding Hamiltonian, and of course from this Hamiltonian you can get the energy, two bands energy as plus minus t mod of f of k. Okay, so this is the energy expression which has been plotted here. So roughly it looks like this. Okay, okay, I must actually, sorry, I am opening this one actually. Yeah, sorry, this was not full screen mode. Yeah, okay. So once you expand this fk, so basically expand f of k around k and k prime, where k and k prime you can found some, there will be some coordinates of k and k prime. So it is 2 pi by root 3 a 1 0. It depends on the system, I mean the coordinate system that you choose, but so these are the coordinates. So if I use different color, then So these are the k and k prime, okay, k prime and k. So if you expand around this, you will get something like so epsilon will be actually linearized, meaning so you will get plus minus 3 a t by 2 and qx sigma x plus qy sigma y, okay, and this qx is simply nothing but kx minus k x. So I should be more careful. So q vector is nothing but small k, this is the block momenta, minus k, okay. So this is the capital K, this is the position of Dirac cone position, and so you can find that these positions, one of the k is given by 2 pi by a root 3 and 2 pi by 3a. So this is one of the Dirac cone, and then another one is k prime, where it will be 2 pi by a root 3 and minus 2 pi by 3a, okay. And there are other equivalent Dirac points. So there are only two equivalent Dirac points. So rest of these are actually I mean there are two inequivalent. So these k and k prime are inequivalent, but rest of the Dirac cones are actually equivalent, okay. Okay. So now we will derive the Landau levels in graphene and we'll see how I mean it varies with magnetic field and so on. So we previously have seen that for 2D free electron gas, so 2DEG, let's say, we have a Hamiltonian like p square by 2m, which is px square plus py square by 2m, right? And the Landau levels are epsilon n, which is given by n plus half h bar omega c, where omega c is eb by m, right? So this was the Landau levels for a free electron gas, where the Landau level energy, so Landau level LL energy linearly varies as B, and then difference between two consecutive Landau levels epsilon n plus 1 minus epsilon n is always h bar omega c. So this is, so if we plot with respect to k or something like this, k momentum and epsilon n, so this is independent of k, so they will be perfectly flat bands. So this is, let's say, 0th Landau level which have energy h bar omega c by 2, and then this will be 3 h bar omega c by 2 and so on, 5 h bar omega c and so on, okay. So they do not vary with the k. Now if we if we fix one of the Landau level, so let's say I am talking about 0th Landau level, okay, and then see the variation of so epsilon 0 versus b. So it simply linearly grows, right? So epsilon 0 or in fact any epsilon is n is proportional to magnetic field. So this linearly grows. Now in the case of graphene, we will see there is a huge difference in both of these cases. I mean, so this is not true for uh, graphene Landau level, where Landau level energy is not proportional to B, rather it is proportional to root B, okay. Epsilon L is proportional to root B, and then the gap, or let's say the difference between two Landau level epsilon n plus 1 and minus epsilon n, in this case at a fixed magnetic field it was fixed for anion, meaning if you take epsilon 1 minus epsilon 0 at some fixed magnetic field, it will be something which is equal to epsilon 2 minus epsilon 1 and so on. But for the case of graphene, epsilon n minus epsilon 0 is not equal to epsilon 2 minus epsilon 1, meaning the gap between the two Landau levels at fixed energy is not same. Okay. And that is evident from this expression itself, because if epsilon n is proportional to root b, and it is actually, there are other factors, but root n b. Okay. So, if you take epsilon 1 minus epsilon 0, then it will be root b minus 0 simply, right. So, it is proportional to root b, and then epsilon 2 minus epsilon 1 will be root 2 b minus root 1 into b. So, it is actually proportional to root 2 minus 1 into root b, right. So, these are not the same. So, here epsilon 1 minus epsilon 0 you are getting coefficient of 1, let us say. Here you are getting root 2 minus 1, which is not exactly 1. So, that we will see in the next few minutes. Okay. So, before that, if you have any question or any confusion, I mean, yeah, any queries you can ask. So, any questions? Okay. So, just a second. Yeah. Just a second. Okay. So we'll do or we'll derive the Landau level expression for the graphene Hamiltonian with the low energy model only. In fact, analytically you cannot solve for the Landau levels once you consider the tide binding Hamiltonian. It is too much complicated. So if you see the tide binding Hamiltonian, it is all over. It is e to the power ikx and iky is there. So you cannot really, at least analytically, you cannot quantize it so easily. So we'll derive it for the low energy Hamiltonian. Okay, and for low energy Hamiltonian, so we have so the Hamiltonian is given by Vf xi qx sigma x plus qy sigma y. So xi is the Valley index. It can take plus 1 and minus 1. So let's say xi equal to plus 1 implies it is k Valley, and xi equal to minus 1 implies it is k prime Valley. Okay, and Vf is that parameter 3a t by 2. Okay, so this is the hopping parameter t, and then a was the lattice constant, and again qx or in general q is block momentum k, small k minus capital K, let's say. These are Dirac, k Dirac point. Okay. Okay, so this is the I mean zero magnetic field Hamiltonian. Now when magnetic field is not equal to 0, so this can be actually, this can be one of the problem in the exam. I mean, I do not know what kind of problem will be given, but since we have already solved for 2D free electron gas, it is natural to ask for the at least 2D graphene case. Okay, so when B is not equal to 0, so we have a Hamiltonian, we can write as Vf xi Valley index, and then so we'll do the Peierls substitution. where we'll take so EA, or rather in general it is written as pile substitution is written as P goes to P minus EA, okay, and A is the vector potential for the magnetic field, or rather it is plus A, because actually in general it is P minus QA. Q is the charge, it can be positive and negative, but for electron then it turns out it will be equivalent to P minus or rather plus EA, right, because Q equal to minus E for electronic case. So Px minus Ex, I don't need any vector, and plus Py minus Eay, and of course there was sigma x here and there was sigma y. Okay, so what we have done in this equation is that we have switched from Qx and Qy to Px and Py, okay. This is just for convention, it's absolutely fine if we write in terms of Qx and Qy, just convention. Okay, so now we need to choose some gauge for this vector potential. So A is vector potential, and curl of A is given by B, will give me magnetic field. And so let's choose the vector potential as minus By 0 0. So this is called Landau gauge. So if you do curl of it, so just as a consistency check, so curl of A will be simply I cap, j cap, k cap, del x, del y, del z, and then you have minus By 0 0. So I and j component will be all 0. You will only have k component, which is del x of 0 minus of minus, so del y of By. So this will be simply B k cap, right? And you can also choose A equal to 0 plus Bx 0. So both of these, so this choice and this choice are Landau gauge, okay. And you can also choose the symmetric gauge, which is A is given by minus By by 2 plus Bx by 2 and 0. So this will also give you same magnetic field, but solving with this symmetric gauge becomes a little bit different. You have a different wave function. In this case the wave function will be of angular momentum when you solve the Hamiltonian. So let me call it HB, impedance of finite magnetic field. So wave function of HB for symmetric gauge can be expressed as that of angular momentum. Angular momentum L that we have read in basic quantum mechanics of Griffiths and so on. But for the Landau gauge case, things become a little bit more easier in a sense that it can be expressed as, I mean the wave functions can be expressed as that of harmonic potential or Hermite polynomial. So Hermite polynomial or of harmonic potential. Okay, so things become a little bit easier, but one important thing is that in both the cases the energy eigenvalues, which are epsilon n, remains same in both approaches for both gauge choice. For the vector potential A. Okay, and that is also because the gauge should not actually determine the eigenvalues of a system. Gauge simply determines or changes the wave function, and wave function are always correct up to some gauge. We can always include some gauge in the wave function in such a manner that it will still give me same energy eigenvalues. So the simple statement is that if we have H psi of a general quantum mechanical Hamiltonian, we have some, let's say, energy eigenvalues and then psi. It is possible that some psi tilde will give me same energy, where psi and psi tilde uh, differ by some gauge. Okay, in fact any physical quantity doesn't depend on the gauge choice. Okay, it is not true that it doesn't depend on the wave function, meaning there are two I mean a little bit subtle issues are there, and I mean it's not issue but it's a subtle thing to understand uh, for transport at least. So it is not that the transport coefficient or the transport response doesn't depend on the wave function properties. It actually depends. For example, in last lecture we have seen that Chern number for some kind of system can be non-zero, in some other system can be 0, and which of these, I mean in which case the Chern number, or the, I mean in only case it is called uh, Winding number, it it is trivial or non-trivial can be understood just by having a map of wave function, right? So it actually depends, but those are intricate issues, let's say. So in fact Berry curvature is one of the thing which depends critically on the wave function. Okay, so that's anyway, that's was a, I mean distraction a little bit, but let's come back to the Hamiltonian in presence of magnetic field. So we had a Hamiltonian. So this was the Hamiltonian. So if we write it, so let's assume xi equal to 1 for simplicity. We can exactly proceed and do that for xi equal to 2 also. So we take some h b psi equal to E psi or epsilon psi. This expression we need energy, right? So we have Vf. I took xi equal to 1, that means sigma x px minus Eax, and there is no ay, so our choice is that it is minus by and 0 and 0 plus sigma y py equal to psi equal to epsilon and then psi. So this we can write as Vf sigma x into minus I h bar del x minus E of minus by, so x is minus by, so it is effectively plus by, right? Yeah. And then we have sigma y of minus I h bar del y psi equal to epsilon and psi. So if you see this Hamiltonian carefully, you have one y term hanging here. This means that Hamiltonian is is not translationally invariant along y direction. So Hamiltonian is not along y direction, and mathematically it means that you have a hb, and along the y direction the momentum is py, and they do not commute. That's the simple thing. And you can also we can also see that why it will not commute. So in hb there is a term sitting something like which is proportional to y, right? And y py is not something that is 0, it is I h bar or minus I h bar, whatever it is. So it is actually I h bar, right? So this kind of term is there, will be there when you do commutation with py, and it will not make 0. So, but in x direction there is no x term sitting. The px is there, but since there is no x and px kind of term, or let's say or px or x type of term will not come in the Hamiltonian, or if we commute with the px. So we need to commute with the px of this Hamiltonian. There will be no term like xpx or pxx. So that means it is invariant or translationally invariant along the x direction. So if we have a Hamiltonian which is translationally invariant along some direction, let's say, then along that direction the component of the wave function we can write as simply the free particle wave function, right? So if you remember, if we have H0 2D electron gas Hamiltonian, px square plus py square by 2m, the wave function was simply e to the power I k dot r, where k is simply kx and ky in 2D. Okay, and of course for box normalization we do ly, lx and so on. So in this case our Hamiltonian, our wave function, one part of the wave function is definitely can be written as e to the power I kx x. Along the x direction it is invariant, and by root lx and so on. And another part we do not know what we need to take, right? So this will be kind of form of the wave function, okay? And this must be this chi, which will represent the y direction wave function component. So component of wave function along y direction, this must be a 2 by 2 2 by 1 component wave function, or spinor of 2 by 1 dimension. This is because we just need consistency. So the Hamiltonian is 2 by 2. HB contains sigma x and sigma y. So some function of sigma x and sigma y, let's say, right? So this is 2 by 2 Hamiltonian. So we have a 2 by 2 Hamiltonian, and then we are multiplying it with a 2 by 1 wave function. This total wave function is 2 by 1, and then we have a energy and again 2 by 1 wave function, right? So this cancels out or gets vanished. Let's say 2 by 1 is equivalent to some number which is energy, and then 2 by 1, just the mathematical consistency. So in one of the direction we have a free particle component, no spinor like structure. In another direction, in the y direction, we have a spinor like wave function. Okay, so if I explicitly write this expression, then we have so h cap, let's say I am writing this part only, this part. So hb cap, it's simply in the matrix form. So sigma x is simply 0 1 1 0, and then it is multiplied by minus I h bar del del x minus, or rather plus E b y, and plus v f. So sigma y, which is 0 minus I 0, and then minus I h bar del y, right? And we can choose psi of this form because of the reason that I just explained. So so if we apply hb of psi, it will be vf 0 1 1 0. So you apply this del x on this e to the power I kx, so it will simply return h bar kx, right? So so if I just do, so del minus I h bar del x, if we apply on e to the power I kx x by root lx, let's say, but these are constants, so doesn't matter. And then there is a chi, but chi is a function of I mean it is not a function of kx at least. Okay, so chi will not operate on operated by del x. So this will give me minus I h bar, and this part plus I kx, so this will be simply h bar kx. And this is what the momentum also, because this is a momentum operator acting on the free particle like wave function, gives back me again momentum. So we have h bar kx plus e b y plus v f 0 minus I 0, this we do not have any way to do, del y, and then the wave function is, I am not writing the full wave function, which is e to the power I kx by root lx and chi. I am just writing as a psi itself. Okay, so this can be written as vf 0 eby plus h bar kx minus h bar del y eby minus h bar kx plus h bar del y, and then 0 and psi. Okay, so the effectively our equation becomes h bar psi equal to hb psi equal to some energy that we want to find, psi, right? So this we can write as we can just take out vf and put it in the right side, so that our equation becomes eby. These are just to simplify the expression. Minus h bar kx plus h bar del y 0, and then we have a psi epsilon by vf psi, right? Now let's take the common of h bar, eby by h bar minus kx minus del y. So basically in step by step we are non-dimensionalizing the whole expression, psi vf psi minus kx plus del y 0. Okay, so we'll do another jugglery. 0 y by lb square minus kx minus del y by LB square minus kx plus del y 0 psi equal to epsilon by Vf psi, and where LB square equal to h bar by EB. Okay, so I just took out this part common. Okay, finally we can write h bar by LB. So let me go through one more step. 0, sorry, y by LB, and this LB is, by the way, has a unit of length, so LB square is simply length square. So y by LB minus kx LB minus LB del y okay. So these are so if we write something like this, 0, I do not want to use I, rather let's say some non-dimensional, so I can write it eta, let's say eta minus, I'll explain how do I write this. Psi equal to epsilon by Vf LB, and on the, this is h bar, right, psi, where we have written eta is equivalent to y by LB minus kx LB. So note that this is non-dimensional quantity, okay, because y has a unit of length, LB has a length of unit of length, and so on, and yeah, and del eta is simply so basically we have, sorry, what is happening, so del eta is equivalent to LB into del y, right. Okay, so again this is also non-dimensionalized, as you can see LB has a unit of length and y again have a unit of length. So this is a complete non-dimensionalized expression, the expression, so all of these juggler is just to simplify the expression, and this is also non-dimensionalized actually. So epsilon has a unit of energy, of course, and then this term Vf LB by h bar is also we can write effectively as h bar omega c in comparison with the free electron gas. So if you write that, so what will be, also what will happen, so this is Vf LB is root over h bar by EB, and there is h bar here, so it is, if it is written as h bar omega c, then Vf by root h bar EB as h bar omega c. Okay, okay, so now we need to we are just to solve the energy expression. So what we can do now is that we construct raising and lowering operator. So let's say A is the one of the operator, lowering xi plus del del xi, and A dagger is the raising operator, xi minus del del xi. Okay, so this is similar to the harmonic oscillator that we studied in Griffith's quantum mechanics book. And if we do this commutator, if you take this commutator A dagger is exactly 1, that's how we define. The root 2 was introduced to make sure that A dagger I mean the commutator is 1. Okay, okay, so this we can then write as, so this expression then can be written as root 2 0. So we have A dagger A, so all of these are operators, psi equal to let's call it epsilon tilde, so this one epsilon tilde and then psi, right? And if you so then we need to carefully choose what will be the I mean the spinor part of this psi. So because psi we had a function like to the power I kx into x by root of Lx, and then chi was the 2 by 1 spinor, right, corresponding to the y component of the wave function. Now once we have I mean A dagger here, so the correct spinor we need to choose, which will be a function of y, let's say will be something like phi n minus 1, phi n, and some normalization constant, let's say, in front of it, or we can write here also, that doesn't matter. So in general we have some coefficient alpha beta a normalization constant, so that alpha square plus beta square root over is 1. Okay, and this phi n minus 1 and phi n are actually I mean the wave function for harmonic potential. If we remember correctly, the harmonic potential, in the harmonic potential case also we had a raising and lowering operator of this, exactly of this form. That's why we can write it as a harmonic potential wave function. Okay, so this is the wave function for n not equal to 0. Okay, meaning we have a bunch of energy, Landau levels, discrete energy. N can go from 0 to I mean as high as it gets, and in sorry, in fact n can also be negative. For graphene case it is definitely negative, so n can be negative, 0 as well as positive. Okay, so this wave function is valid for n not equal to 0, but for n equal to 0 something interesting or some more care is needed, because we have a Hamiltonian like A dagger A 0. Now n equal to 0 is the lowest energy level, so you cannot go beyond, I mean, so yeah, so this is the lowest energy level, so that its form is the correct form should be some, again some constant, let me put it beta itself, and phi 0. Okay, why do we need this? So let me explain a little bit more. So so this is, let's say, H tilde. So initially was we had HB, but now it is H tilde. Okay, so if we do H tilde and then act on the wave function, conventional wave function, let's say phi n minus 1, phi n, and equal to energy phi n minus 1 phi n. I am not writing the constant, but you can always write. Okay, and we are searching for n equal to 0, which is a zero energy mode. Okay, so for graphene there is always a zero energy mode, I mean in the Landau level at least, when there is no external gap and other parameters are there. So we are searching for a zero energy, epsilon n equal to 0 equal to 0. Okay, now if this is the case, so we have a Hamiltonian like A dagger A and alpha phi n minus 1 beta phi n, so it will be this part. So this is 0, and then beta A dagger, which is raising operator phi n, and plus A raising operator alpha phi n minus 1. Now since we are searching for n equal to 0 level, so 0 minus 1, so this will basically be so this part is phi 0 and this is A dagger beta plus alpha A dagger phi of minus 1 n equal to 0 case. So so you see that there is, we are not getting the zero energy mode, we will not get, because A is the lowering operator and it will keep lowering this this part, right. So we have raising operator, so I am, let's say, at the lowest energy state n equal to 0 from the positive side, let's say, this part is fine, but this part will keep lowering the energy, so we will not get the zero energy mode once we use this kind of wave function. So for getting zero energy mode, a special kind of spinor part is needed. So spinor part is 0 and phi 0. So this is the 0th year. Okay. So if we take this kind of so let me write for 0th Landau level, or simply Landau level. So we need to choose this chi, and if we choose this chi, then what will happen to HB of psi, let's say HB tilde of psi, then it will be equivalent. So this kind of expression will be there. So again beta A dagger phi 0 plus alpha, and this part is 0, so we will have A into 0. So beta A dagger phi 0. So this can give me the lowest energy state, because so this is already you are touched down at the 0th level. Now as you keep applying Hamiltonian, you can increase the energy levels slowly. So the lowest energy, for the lowest energy level 0, we need this kind of 0th Landau level, we need this kind of wave function. Okay, and this has a peculiar property. So we assume that xi equal to plus 1, which is assumed for k value. Once you do the same calculation for xi equal to minus 1, which is k prime value, you need to choose chi exactly opposite, let's say alpha phi 0 0. So so for one of the values you need to choose this kind of wave function, and another values you need to choose the opposite kind of wave function. And that's why we say that for graphene, the lowest energy Landau level, which is 0th energy Landau level, lies on one of the sublattice actually. Okay, so so either on this sublattice xi equal to 1, or on this sublattice xi equal to minus 1. This is in the pristine case, you have not applied any mass term or any gap term. When you apply gap term, which is, I mean, often considered in realistic system, then of course it can reside on the both the sublattice. So then chi 0 for energy 0th energy level, we can have both the contribution, I mean contribution from both the sublattices actually. Okay. Okay, so anyway, so So this was actually for the zero energy level, but for the n equal to not equal to 0, so we are fine with this kind of expression, I mean wave function and so on. So you will use this expression. So we have root to 0 a or a dagger, it was a dagger, so a dagger a 0, and then alpha phi n minus 1 beta phi n, right, yeah, and then epsilon tilde alpha phi n minus 1 beta phi n, yeah. So I am explicitly not solving the equation. So basically you need to solve the phi n minus 1 expression and phi n expression. So if we solve it actually, so beta a dagger phi n equal to, so we will have two equation, epsilon n tilde alpha epsilon, I mean phi n minus 1, and then root 2 a alpha phi n minus 1 equal to epsilon n tilde beta phi n, right. So let's derive beta, or rather, yeah, beta epsilon n tilde alpha phi n minus 1 by root 2 a dagger phi n, and this is actually epsilon n tilde alpha phi n minus 1 root 2 into a dagger means n plus 1 phi n plus 1. I think there is some inconsistency. Yeah, it's okay. So if I replace this in expression root 2 alpha a dagger is lowering operator, no, I think I have flipped this, I mean representation of lowering and raising operator actually. Yeah, so if we do, yeah, that has been flipped, otherwise so it will keep lowering and it will keep increasing. Yeah, so once we use the opposite convention actually, so the epsilon n will be simply plus minus root over 2 n h bar omega c, okay. So this will be the I mean eigen energies. Okay, so as you can see from this that epsilon n is proportional to or root over n, in contrast to the epsilon n proportional to n in the free electron case. So free electron case it was in n plus half h bar omega c, okay, and epsilon n is here proportional to root over of b, and epsilon n in the 2D EG case it was proportional to b. So there is a, these are the two main contrasting difference, okay. Okay, so this was the derivation of Landau labels for graphene system, I mean low energy graphene system actually. Now okay, so so if you have any question then you can ask, otherwise I'll be, I mean I'll not fully derive, it will take a lot of time actually, but I mean I'll just state the process and some in between steps of how to derive that Kubo formula for conductivity. So that was one of the question in assignment 2, I mean assignment 4, sorry. Okay, so derivation of Kubo formula for conductivity, yeah, it's pretty involved actually. So we need advanced topics like Matsubara formalism and so on. But I'll just briefly go through that. Okay, and yeah, just give a glimpse of how it comes about. So you have actual Kubo formula is given by mu nu, let's say some finite frequency response 1 by omega. Omega is simply volume of a 3D system, or it can be area for 2D system and so on. 0 to infinity dt to the power I omega t, 0 to beta d lambda, trace of rho 0 j nu. So nu and mu is the spatial indices, and then minus I h bar lambda j nu of t. So basically the trace of this rho 0. So rho 0 is the equilibrium density matrix for the system, and j nu is the current operator. So let's say j nu is current operator, or so this part j nu minus I h bar lambda is given by e to the power lambda h 0, lambda is some parameter, j nu. So this one is the current operator, e to the power minus lambda h 0, and for j nu of t we have, so this is in the Heisenberg picture, I h 0 t by h bar, h 0 is the Hamiltonian, j nu again these are operator minus I h0 t by h bar. Okay, and if we go to the zero temperature limit, DC limit, we can show that sigma xy is actually, we should take it as a omega goes to 0 limit 1 by omega imaginary part of 0 to infinity dt e to the power I omega t, and then expectation value of jxt and jyt, jy0 actually. So jy is at a 0 time and jx is at a time t. Okay, so so this is actually the zero frequency limit expression. Now if we want to derive Hall conductivity in the DC limit, let's say, or yeah, so from the linear response theory, the derivation of this expression itself is pretty big. Okay, so I am skipping that. Rather, I am showing that how Hall conductivity comes about. That nu e square by h from this basic equation, let's say. Okay, so assume that we have applied magnetic field in the 2D free electron gas system. Now we are in the 2D EG system. Okay, not in the graphene like. So again we will choose minus by 0 and 0, and velocity operator. So we have a Hamiltonian like px square by 2m, or rather, or let me choose the different gauge also, it will not affect the result. 0 bx 0. So then the Hamiltonian will be px square by 2m plus py ebx square by 2m. Okay, then velocity x component will be simply px by m. Velocity y we can easily derive that it will be py plus ebx by m, similar to this case. Okay, so this is simply these are operators, of course, del h, del p, let's say. So velocity operator is simply del h del p. Okay, and then current operators are along the jx we have minus e vix, or simply in our case it is just the vix, vx actually. Jy is again minus e vy. So then the operator, I mean commutator of jx and jy, jx and jy is equivalent to minus e common and then vx vy, right. So So this will be plus E square minus E into minus E. So the Vx and Vy, so we have Px, I am taking common of M, and then Py plus Ebx, again M, another M square. So E square by M square. So we have Px Py plus Px, so Eb is Eb, and then X. So E square by M square, this part is 0 plus Eb X of Px is minus I H bar. So this is simply minus I E cube by M square H bar B, right? Yeah. Now what do I need is that this part Jx of t, Jy of 0, and then expectation value. So expectation value is nothing but trace of these, the same thing basically. So trace with rho 0 and then the same operator. Okay, and it can be shown that in the quantum Hall regime, this part actually gives some topological contribution. So this commutator actually gives topological contribution. Okay, in terms of that filling factor nu, which is also related to the Chern number and so on. And then once you do this integration 0 to infinity dt e to the power I omega t, expression of, I mean expectation value of jxt jy0, it will be equivalent to I omega e square by h nu. So this we can actually derive using poles and so on. Okay, the residue theorem and so on. So once we have this imaginary part of this part, whole part, is simply omega e square by h nu. Nu is that again filling factor. So then sigma xy is limit omega tends to 0 1 by omega e square by h nu, which is simply e square by h nu. Okay, so this is the quantized Hall conductivity. Okay, okay. Okay, so the rest of the problems are actually uh, not new, so I'm not solving those problems. But another interesting point before closing, of course this is not related to that Kubo formula and so on. So we had so Hamiltonian, Dirac Hamiltonian for the graphene, we can simply write as Vf Qx sigma x plus Qy sigma y. So this is, let's say, for one of the values xi equal to 1. It can also be xi equal to -1, so then we need a -1 here, right? Okay, now in convention, and then this has a energy expression of h, not h bar, so Vf simply q, right, mod q, where mod q is root over qx square plus qy square. Okay, so this is plus minus k, let's say. Now in contrast to this, for free electron gas we had a I mean energy expression something like this, h bar square k square by 2m, right? Q we can take as equivalent of k for simplicity, so let's write as k simply. Okay, so then this is also just for same comparison. Okay, ky square. Now for free electron gas we have the concept of, in the band theory we have concept of effective mass, right? So h bar square del 2 epsilon k del k2 of inverse of that, right? Now for free electron gas we have del epsilon del k, let's say, which is h bar square k by m, and then again if we take another derivative, k2 equal to h bar square by m, right? Then it becomes h bar square and then 1 by h bar square of m, so it is equivalent to simply m, which is true also for free electrons. The effective mass is itself this part, this mass written here in the energy expression. In general, as we go different parts of the band in the Brillouin zone, for a general solid state system the effective mass deviates from the electronic mass and so on. Okay, and it can also depend on the k itself, momentum. Now if we apply the same formula, so you see what happens. So for graphene, so this expression del epsilon del k itself is 0, so that means del epsilon del k2 is, sorry, del epsilon del k is simply Vf, right, plus minus Vf, let's say. So then it is 0. Now if we use the same formula m star h square del 2 epsilon del k2 inverse, so basically h square by 0, so it blows up, it goes to infinity, so the mass, effective mass goes to infinity, right? But then we call it a massless Dirac fermions, right? So what is happening here? So if you use the conventional formula, you are getting mass infinity, mass goes to infinity, and then we call massless Dirac system or Dirac fermions for the graphene. Right, so what is really happening? in conventional expression we are getting mass goes to infinity, but then we call it massless. So it turns out that we need to remodify this expression actually for when we apply to the graphene like system. So for graphene like system we actually make things consistent by the following way. So we have a momentum equal to h bar of k, right, h bar of k, and this we can think of as a effective mass times group velocity, right. Now we will backtrace what will be the effective mass from this expression. Okay, how do I derive that formula? Now Vg is something del epsilon del k, group velocity. So then m star can also be written as h square k del epsilon del k inverse. So this expression is for graphene actually, or massless particles. How do I see that for massless particle it will be the case? So we have epsilon equal to Vfk, let's say, right. Then m star becomes h bar square k, and then del epsilon del k is simply, so del epsilon del k we have derived simply Vf, right, Vf. Now as k goes to 0, m star goes to 0. Okay, so then it becomes consistent with the graphene's definition, or what we say that m star is proportional to k. So that the Dirac fermions becomes massless basically. Okay, for graphene, and this is around the narrow region of k, or around k or k prime Dirac points basically. Otherwise it's a massive particle. Okay, and this is also kind of, you can see from the relativistic Dirac equation actually. In the relativistic Dirac equation we write as p dot c plus beta m0 c square, right. So this term we do not have. For graphene Hamiltonian we simply have Vf sigma dot k, right. So we can write as k dot sigma. Okay, so this part is there, but there is no m0 equal to 0 for graphene case. Okay, and massless doesn't necessarily mean that its velocity is actually the speed of light. Okay, so for relativistic cases in quantum mechanics or high energy physics we have velocity is definitely equal to c equal to speed of light, let's say, right. But in our case the graphene's velocity is of the order of 10 to the power 6 meter per second actually, instead of c which is of the order of 10 to the power 9 meter per second. Okay, but we still call it massless in the condensed matter perspective. Okay, so we'll stop here. If you have any question, again I just ask as usual, you can just email me at sunidhi@iitk.ac.in, and there will be a regular tomorrow's class as well. Okay, so this was for compensation class for week 4. So I was not I was actually attending conference, so I couldn't take it. So there will be a usual tomorrow's tutorial from 6 to 8 itself.